everybody, and welcome to Linear Algebra with me again. We're going to be doing matrix operations today. We've talked about vector plus a vector, matrix times a vector, but we haven't done anything with two matrices yet. And that's what today is about. So first off, I want you guys to recall for me real quick that we have written matrices efficiently. We've used some vectors to efficiently write n by n matrices in terms of columns. That guy right there. But we don't have to write it that way. Sometimes it's better to write it entry by entry, and we have a notation to write it entry by entry. And so that would look like saying A1, A12, all the way up to A1n. And notice that 1 stays constant, that first entry. It's 1 all the way through, because that 1 represents row 1. And then the columns, so this guy, that guy, that guy, the columns are all changing. And you're like, oh, okay, so like I said, m by n matrix, m is rows, n is columns. All right, checks out. I buy your story. And then if we go down, we've got 1, 1, 2, 1 all the way down to m1. That's because the columns are staying constant here. This is column 1. We are looking at the second entry, and that entry represents column 1. So if we were to talk about the entry Aij, this would be equal to the entry in row I and column J. Okay, so writing it term by term is going to be useful for defining some of our matrix arithmetic things that are about to come. It also gives us an even more efficient way, turns out, to write our matrix. This guy right here. We can shorten him way the heck down. Okay, so we're going to start off by defining what it means for two matrices to be equivalent. We're going to say that matrix A will equal matrix B if they are the same size, which that makes sense because you can't have something equal something else and they're different sizes. Like, where's everything going to go? And Aij equals Bij. That just means every single entry is the same. Next definition I've got for you is the main diagonal for an m by n matrix A are all these entries where the row and column are the same. So even though we have like rectangles sometimes, we still have a diagonal. And then we call a matrix a diagonal matrix if it is n by n, by which I mean same number of rows, same number of columns, so it's a square, and the only non-zero entries are on that main diagonal. So for instance, we have IN. He's got 1s on your diagonal and then 0s everywhere else, like that. So classic example is, or a classic diagonal matrix would be the identity matrix. Other things to think about, like you could also say that reduced echelon form, you know how you have to get your diagonal and then everything above the diagonal is also going to be 0. That would be another diagonal matrix. And so our goal when we're solving these matrices or matrix equations is to get them into a diagonal form. Okay, so let's move on to matrix arithmetic. We're going to have A and B. They're both n by n matrices. They are the same size, just in case I didn't point that out before. Scalar multiplication, you have C times A equals C times AJ, or AIJ, and that translates to just multiply every entry. And then addition and subtraction, you've got a plus or minus b is equal to little a plus or minus little b, and that's going through and you add up all the corresponding entries in A and B. So like the very first entry in A, you're going to add that with the very first entry in B. All right, so now that we know how to add and multiply a little bit, we have some properties of matrices for you. We've got A plus B equals B plus A, just like we did with vectors. You can prove all of these component-wise, just like I did with vectors. We've got associativity. We've got A plus 0 equals A, where 0 is the zero matrix, aka it's a matrix full of zeros. And then you can distribute a constant between two matrices. You can distribute a matrix between two constants. And it doesn't matter how you multiply your constants in. You can multiply them first outside and then multiply them in, or you can multiply them in one at a time. Both work. Okay, so let's just take this for a test run. We've got 2 times a matrix plus another matrix. First thing we want to do, let's distribute that 2. So 2, 4, 6, negative 2, negative 14, 20, not 10, plus 8, 0, 7, 1, negative 10, 4. And then when we add these up, like these two guys, those guys go first. So the result there is going to be 10. The next ones to go are going to be, it doesn't really matter what order you go in. I personally prefer to go through by columns simply because it helps me write more neatly. Okay, so next one that we're going to do is 4 and 0, which is going to be 4. And then we're going to do 6 and 7, which is 13. And then we've got negative 2 and 1, which is negative 1. Negative 14, negative 10, negative 24. And then 20 plus 4 is 24. And then, yes, this is right because I checked myself in Mathematica. Haha. Okay. Matrix multiplication. We have not talked about matrix times matrix yet. It's not as intuitive. But here we go. Okay, so definition. We've got A is an n by n matrix and B is an n by p matrix. We call the matrix product between A and B the matrix we get when you do just the first column of B times A, and that's your column 1. And then column 2 is just the column of B times A. And we do it this way because we've done matrix times vector. Let's see. So remember that A times BI is going to be a vector. I'm just going to write this down. A times BI is a vector. But where does he live? Let's see. So just one of the B's is going to be an n by 1. And so m by n, and then this one was n by 1. And so we get an m by 1 overall. But then we have p many columns in our result. So first off, number 1, notice A needs the same number of columns as B does rows. Okay, so that's number one. The reason for that is the exact same reason we needed the same number of entries in a vector as we did columns in A. Okay, so that one shouldn't be a shocker. And then the second thing I'm going to point out is when you have A times B, A is going to be an m by n matrix, B was n by p, you get this result AB, and where does he live? Well, I already said that the result of A times B was going to be m by 1. Give me one moment. So if A times one of the columns in B is going to be m by 1, that means our result here, A times B, those are all going to have m rows as well. And then I already pointed out over here that we've got p columns, and so it ends up being an m by p matrix in the end. So when you're multiplying, first thing you always want to check is, does that inside value match? And then whatever your result is going to be the outside too. All right, so you can think of matrix multiplication as going through and doing A, and then all of A times B1, and then A again, all of that times B2. But let's stop and think about what you're going to get out. What is the very first entry going to be in this result? Okay, very first result or entry is going to be the result of the very first entry in just A times B1. So that's going to be the top row of A times all of B1, which is what I have highlighted down here. So you've got A's times B's gives you this first entry. Notice I'm not doing row times row because B1 is a column vector, not a row vector. And we already discussed how we take a vector that is a column and we multiply on the rows. So same deal with matrix multiplication because vectors are just really skinny matrices. And then to get another entry, so let's say we want to get C2, 1, so that would be this guy right here. If we want to get him, what we want is second row, first column, because this is in the second row in the first column. I'm going to write that down real quick. So Cij is going to come from multiplying A's row I times B's column J. Okay, and to this day, like the quick way to think about it is, so you've got your A matrix. I have to orient this for you guys. You've got A and you've got B, and I just move up. I'm like, oh, bring it up like that. Boop, 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 all the way through. And again, I prefer to go through like the first, I would go through the results first column, just because I think it helps me write more neatly. But if you would rather tackle the entire first row, that is okay. And I'm going to show you an example of how I would multiply all this out. Oh, but I did have this really cool application for intuition from a programmer's perspective. Remember, like when we have, I'll be up here. when you have A times B, remember, like, we spent a lot of time using A to represent systems of equations. And then the vector X would be like whatever input we want for those system of equations. So if you line up a bunch of them, that just means you would have, like, essentially for a computer, a bunch of data. And you're putting all those into our equations or operations, and you get out some information. And so you feed one in, and it has to go through each one of these. And then that gives us our first piece of information. And then you take our second one, and you have to feed him through all the operations to get another piece of information like that. I thought it was a cool way to think about it. There is an in-depth version of this discussion that is in the book, and it involves, remember, we did linear transformations, and those were functions. It involves composition of functions, but I don't know. I didn't find it like that enlightening, and so I'm not going to discuss it. What we are going to do is we are going to do an example, because I feel like this is much better once you've seen it in motion. So if we want to find A times B, what we're going to do is I first write out 2, 4, 1, 1, negative 1, negative 2, 3, 0, 3. And then we've got 0, negative 3, 2, 5, 2, 4, 1, 1, 8. And that is equal to, first entry comes from row 1, column 1. So if we multiply those together, that's going to be 2 times 0 is 0. Negative 3 times 1 is negative 3. 2 times 3 is 6. So there we go, first entry. Then next, I want this entry here. So row 2, column 1 still. So column 1, but row 2. So that's going to be 0 plus 3 plus 0. No, yes. I love zeros. They make things easy. Okay. And then the next one I want to go after is this entry. So row 3, but still column 1. So we need that row. So here we go. We've got a 0 plus 6 plus 6. Okay. And that's all of column 1 for our result matrix. Now let's go after column 2 of our result matrix. That's going to require column 2 of our B matrix. So to get the first entry, we need the first row. So row 1 times column 2 is going to be 10 plus 2 plus 12. And then we've got the next entry going down. We want to go down in our A matrix. Because remember, rows correspond with the rows of A and columns correspond with the columns of B. I'm going to say that a million times and hope that it goes in. 20 minus 2 plus 0. And I miss in-class things again because I would start shouting like, okay, shout out entries to me so I know you're following, please. Okay. If you can shout at your computer, I'm sure I can feel it in spirit. There we go. Okay. So that is column 2. Let's do column 3. So we need third column of B, and then the top one is going to come from the top row of A. So then 2, 1, 24. Then we move down a row. So we move down a row in A. So 4 minus 1 plus 0. And then down one more row. So now we are in the last column in the last row, and that gives us the last entry. How fitting. So 1 minus 2 plus 24. And then when we do out all that arithmetic, you end up with 3, 3, 12, 24, 18, 13, 27, 3, 23. Assuming that I haven't messed up drastically. So challenge to you, did I mess up? Please tell me. Okay, so that's our example. Hopefully that's okay for you guys. Let's do another one, but it's not going to be square. So this time we've got A is tall, B is short and wide. Okay. So we're going to go after, well, quick dimensional analysis, since now we're not dealing with squares anymore. This guy is 3 by 2. This one's 2 by 3. The insides match. Good, good, good. So what size are we going to get out? 3 by 3. Cool. Okay, first entry. First column, first row. That is going to be 1. So 1 times 1, 0 times 0. And then the next entry, we multiply by this row, and that is another 0. And then we multiply by this row, and that is another 0. And then we need to move columns. Oops, come back one. So then second column, row 1, that's going to be 0 times 1 and 1 times 0, so it's 0. And then the next one is going to be 0 times 0, 1 times 1. And then last one is, of course, 0 times 0, and then 0 times 1, so it's 0. And then last entry, you've got a 0, 0 here, and so I'm sure it's no shock that all of these are 0. Okay, so that's A times B. What if we do B times A? So let's write this out. So B is 1, 0, 0, 1, 0, 0. 1, 0, 0, 0, 1, 0. This guy is a 2 by 3. This one is a 3 by 2. The insides match. Good, good. And that is going to end up being a 2 by 2 then. Okay. So then let's start out. First column, first row. You multiply the 1s together, and then the 0s all multiply together. And then we're going to do the next row. And now the 1 is being multiplied by a 0, so all of those are 0s. And then we have to move to the second row. And we do the first row and we get a 0. And then we do the second row and we get a 1. Okay. What is the huge difference between the result for 1 and the result for 2? They're not even the same size. So if I were to ask, does it matter which side you multiply them on? The answer is hell yes, it does. But if you don't have square matrices, you might not even end up with the same size matrix. And even if they were squared, trust me, the results are not going to be the same. Okay. So now that we've clarified that, please don't forget, the math police will come for you. But now we've got some properties of specifically matrix products. So we're going to assume that A, B, and C are compatible sizes. And I'll talk about what I mean by that in a minute. And then D is a scalar. So for instance, here, you would need to have the number of rows in A match the number of columns in B, and the number of columns in B matches the number of rows the number of rows in B match the columns in C. That way you can multiply all those guys together. Second property, now we have B plus C. Now we need B and C to be the same dimension. We don't care so much about rows and columns matching. We care about rows and rows matching and columns matching. So that's what I mean by compatible. So we've got distributive over multiplication or over addition. We have it doesn't matter which order you multiply them in the fact that you could do whichever of the two matrices that you want first, just as long as they stay in the same order. You know, like ABC instead of BAC. And then scalar, you can multiply the scalar first, or you can multiply him afterwards. It doesn't matter once again. And then when you multiply A by the identity matrix IM, because I'm assuming A is M by N, and so you would need to be able to multiply it on the left by IM and on the right by IN. You're going to get A either way. Okay, things to be careful of, things that people mess up on. We just covered it. AB does not equal BA. And just because A times B equals 0, that doesn't mean that A equals 0 or B equals 0. You might have two non-zero matrices but still end up with a 0 result, which is really weird. That's not how numbers work at all, but that's how matrices work. And then lastly, A equals C does not equal, or AC equals BC does not mean A equals B. Once again, that's not how numbers work, but that is how matrices work. Okay. Flipping to a different kind of a topic, transpose of a matrix. So let's say we have an n by n matrix, just like we've been doing. We'd say that the transpose, denoted by A to the T, is an n by m matrix. Notice that those are flipped. The n by n matrix whose, typoed. I've got it twice. Is the n by n matrix whose columns correspond to the rows of A. What do I mean by that? Well, I've got a little chart with 4 different examples. So here is a row of A. Here is a column of A transpose. Yes, they are the same. That is on purpose. Here is another row of A. Here is another column of A transpose. Yes, once again, they are the same. So going back to the words, we've got, given a matrix A, the transpose is the matrix whose columns correspond to the rows of A. So basically, rows and columns switch jobs. And then I'm going to take the transpose. So we've got this guy here. He's actually this guy here. So if we take the transpose of him, that row becomes a column. And notice we've circled back to that guy. That's actually one of the properties of transposes that you're going to see on the next screen. And then last one, that row is this column. What's with the circled things, Gracie? Why did you circle them? The upper left and the lower right always stay in the same point, same spot. They're never going to move, ever. Because, for instance, this row, highlight, come back. This row becomes the first column. So first row is now the first column. That means the first entry doesn't switch locations. And so the way I do, is this the right way? Yes, this will work. This will work. So the way I do transpose is like if I'm sitting there on an exam, I'm just like, oh, how do I do this? I literally sit here with my hand and I'm just like, okay, so the corner and the corner and then I flip and the corner is still here. So this corner stays, and then the other corner. I'm not sure that translates going backwards. So you've got your m by n, so this should stay the same. That is the wrong corner for you guys. Hand trick. Okay. We're going to do it this way. So you've got your matrix, you've got this corner and this corner. They're supposed to stay the same. And so if you flip it over like that, so you've got a long matrix would become a tall matrix. This entry stays the same, this entry stays the same. But notice this entry and this entry switched places. Okay, I don't know. Maybe that visualization will help you, maybe it won't. But let's discuss some properties of matrix transposes now that we hopefully know what a matrix transpose is. Once again, we've got A and B need to be compatibly sized matrices depending on if we're adding or multiplying them. So the transpose of a transpose is going to be equal A. That's because you have, just like we saw in these guys, rows go to columns. And then what happens is those columns get mapped back to rows. Okay. And then the next one is intuitive. If you add two matrices together and you take the transpose of that, you can just take the transpose of the matrices first. Scalars, they don't get hit by transposes. And so you can do the transpose before or after because you're going to multiply every single entry by the scalar anyway. And then 1 through 3, those are like pretty easy to prove. I think it kind of works intuitively. The fourth one, not so much. But you're like, why did they switch places? So let's look at the dimensions again. So we've got an m by n, and n by p. So overall, it will be m by p transpose. So in the end, it's a p by m. And then we've got b transpose times a transpose. So the b transpose is a p by n, and a transpose is an n by m, and you put that together and you get a p by m. So the dimensions match up. Indeed, if I hadn't switched the order of b and a, so that they're backwards from before, you wouldn't get this n and n on the inside matching dimensions thing happening. And so you wouldn't be able to multiply them at all if you just straight took the transpose in. Okay. So that, I think, wraps up matrix operations. We talked about adding them, which was easy. We talked about multiplying them, which was less easy. And we talked about transposes, which was kind of weird, but I don't think it's as bad as multiplying. Multiplying requires a lot of good bookkeeping. So that being said, I think that's all I've got for you guys for today. So I will see you all next time.